hearing about my work all through the years. So without getting late, let's get started to today's session. So just to give you a brief about today's session, the idea behind today's session is to make everyone aware of the role of a design engineer on a day-to-day basis. What you can expect if you would like to be a aesthetic design engineer. I'm pretty sure the distinguished guests from the last 2 days we have spoken a lot about the flows, a lot about what happens with the industry, and a lot of those insights would already have been uh, a lot of things would have already been said to you. Uh, so let me also go you with a few of those facts once again. So today's agenda will be kind of a path from classroom to being a chip designer in the real-time world. Okay, so that is the kind of key you can say for this particular session. Going ahead, the agenda. These are a few basic things that I would like to cover before I talk about a lot of other things as well. So the first thing is I would like you to give a sneak peek into the semiconductor industry. I'm sure a lot of other guests would have also done that, but I would like to present my perspective here. Along with that, let's speak a bit about the semiconductor value chain and where exactly we as design engineers fit in this value chain and what can we contribute to this. Moving ahead, how to be a design engineer. So that is like a very key question. Like, okay, you're speaking so much about all of these things, but if I really want to be a design engineer, what can I do differently to be that? So let me cover something on that. What are the required skills? What is the educational part? What is that you can do in the classroom so that you can come out and be as a chip designer in the industry? So a little insight to that. What kind of internships, what kinds of projects you can take up for you to get into that path, and what to do in college. So, what is that we can do to utilize this time that we are spending in college? Of course, have fun, enjoy your college life, but a little bit of this as well. Just to motivate you in terms of the salary trends and the growth opportunities that we have currently in the Indian semicon field. So that is also something that I would like to walk you through. And finally, definitely, there are lots of challenges to enter the industry, but it is not impossible, but it is a little tricky, I would say, not even tough to enter the industry. So, what is that you can do to overcome these challenges, and what are the future plans that you can experience in the semiconductor industry? So, first half an hour or so, I walk you through all of these things, and later we can jump in and do a bit more, little more technical stuff that I will bore you with. Okay. Okay, so just a quick introduction. So you all know what is semiconductor, what are semiconductors, and why it's important. So everything that you are using from your phones to watches to everything that you are using has a small PCB or a small IC. Everything is related to the semicon industry. Some engineer like me and you are designing these. Okay. What are the major global players? I'm pretty sure you would have heard all of these things. So you're welcome with your mobile chipsets, maybe with your gaming consoles, Xboxes, PS5s. Your NVIDIA is like your go-to graphic cards. They are accelerators these days. Samsung again is your phones, laptops, lot of these things. So these are just like a tip of the iceberg of the ocean of the companies that you will explore in the semiconductor industry. Okay. And what is India's position in the global market? So this is one thing that I would like to spend like 5 minutes to explain you. A lot of people have a lot of misconceptions about the semiconductor industry. We don't have enough opportunities in India. It's a very slow market. You have to be a master's graduate, or you have to graduate from top colleges, premium colleges, IITs, triple IITs, or you have to go abroad to gain entry into semicon industry. Yeah, to some extent, all of that is true. But on the flip side of it, I was studying here in Vardhaman, today I'm standing in front of you years with the after 16 years. So what I would like to say is that if you focus on the right direction, have the right tools with you, understand the market, it is not possible for you to gain access to the market. Okay. So back then, like when I started my career, we didn't have the kind of access you guys have these days. So if you already have the set of tools in your hands, you just have to know how to use them correctly. That's all. That's all it takes for you to understand and how to get into the semiconductor industry. So coming to the global market, as we have seen, India is one of the top skilled Asia's go-to place. So all the semiconductor companies are now looking at India to be their major design centers. From the last 5 6 years, you see lots of companies, all the big companies have their R&D and design centers in India. So opportunities wise, there are lots of opportunities. I myself struggle to fulfill the opportunities that come to us from our clients or for me to fulfill in my team. So, but we move the negative side of it is like we have a huge skill gap. So that is what I'm trying to do here to bridge that skill gap, which from my end to whatever extent possible between the college to the industry. Okay. So I'll try to give you more insights on how you could build that skill gap, and what is the things that we are lacking as engineers, as students, and what is that we would be going ahead as real-time engineers needing to get into the industry. Okay. So future trend-wise, we do have lots of opportunities. We have a lot of new startups. We have a lot of US-based companies that are trying to set up their teams here in India. One for the skill, one for the cost-effective solutions. And the thing is that the government, the government is in the lot on the semiconductor industry. You have seen a lot of news going around these days. So all these are drawing a lot of industries towards Indian market. So definitely you have good opportunities. It's just that you just have to work towards it. Going ahead, just to give you an overview of the valuation. So broadly, if you divide the semiconductor companies, you have fabless companies, you have foundries, and you have OSAT companies. And the supporting industries like equipment, material, applied materials, and a lot of those things. Okay. So fabless companies are something that they design chips, so they don't have a fab for them. So all your AMDs, all your media, like all these companies, they don't have fabs for themselves. They approach the fab companies to get their chip design. Let's say you own a company, you design a chip, you are a fabless company. All you do is you have an idea, you make it a design, you make it an end product, and then you take it to some fab chip design. The fab will get your chip ready for you. Okay. So these contribute almost like 80% of the market, 80 to 90% of the market. The foundries, they contribute like 10% of the market, and then the rest 10% is with these guys. So usually these two kind of companies are found either in US or your Korean, Chinese, Taiwanese markets. So these are the major areas where these companies will be found mostly, and these are the fab companies that we will get into. So getting to fab companies is really difficult because the kind of precision and skill that is required and the kind of knowledge you should have at the transistor level and the physics that you need behind it is way too high. I would say like a lot of art colleges also don't have that kind of education that they can drive towards that. But still, there are few premium institutes driving towards it and helping the engineers to get into these kind of things. But once you are graduated, if you are really willing to get into these foundries and those kind of companies, you can pursue your masters in foundries and fabrication, and that is how you can get into these industries. Opportunities are less, people are less. So obviously, it is more like a chicken and egg story. When you have opportunities, you'll have as well as like the demand will also be there. So if you could, if you're rightly focused there, and if you're really interested in that level of transistor, fabrication, and a lot of those things, you could definitely get into these things. But today's major focus will be on this fabless companies and what exactly we do in the fabless companies. Okay. So this is what I want to spend a little time on to give you the insights on how to be an architect. So there is no rule book for it. This is something that I feel is required by any engineer to be a successful design engineer. The first thing is learn your basics. Your digital basics are the must. No negotiation there. Understand your combinational gates, understand your sequential logics, understand how your flip-flop works, understand how your AND target works. That's all. These are the basic gates that you have. This is the basics that you have. Understand it thoroughly. Understand it in the sense that how does the flop work? What happens if I do this? What happens if I do that? So it is not just like two transistors connected back to back. It is not that. So you have to understand what does a flop do, how that can be used in the real time, how it actually used in the real time. To that extent is what you have to build your thinking to. So that is when you have to focus main on at this stage. Is to learn your digital basics. Next, learn to think logically. Okay, so you can ask me, Ramya, this doesn't make sense. How do we do that? I give you a very boring answer for this. It's your math. So whatever the equations, whatever the math formulas, everything that you learn all through your life will help you here. You have to learn math. Math teaches you how to learn to think logically. So all the boring aptitude questions that we solve for our campus interviews will actually help us here. See, to be a design engineer, you should always keep your logical thinking going. You should always think logically. You should always try to find optimal solutions for it. In math, what do we do? You solve a problem, you solve a problem. You get 5 marks, he gets 10 marks. The reason is he might be using a effective approach to solve the problem, whereas you might be taking a difficult route to solve the problem. Ultimately, both of you give solutions, but what is the optimal solution? Let's say for a give you a mobile phone and tell you like, okay, take this phone for 10,000. The moment that you take the phone, what is the first thing you check? You check your camera quality. You check the time, like okay, as soon as I click, you want the application to be opened within a minute. Without you realize. Sometimes you experience that lag in your phones. The moment you guys find that lag in the phone, you can simply toss it off and go and buy a new phone. So that is the difference between being a design engineer and being a design engineer. Got it? Because at the end of the day, the user will not understand what is going to be. But you as a design engineer have to think the moment you start designing something, you have to start thinking at the end, how will this translate to? How will the end user have the touch and feel of the design that I'm doing? Let's say, for example, you are designing a chip for some flight, which is going to be a part of some flight communication system. You don't give an optimal solution. There are thousands of lives at stake with that, correct? You go to that system. So your car safety and people's lives are at stake. So since there is a lot of money, there is a lot of real-time solutions that we are providing, getting in the industry is also difficult. So you are understanding, right? So it is a direct proportion that since you do something that is going to affect people's lives in the real time, for you to be a design engineer, you have to be the best of the best. You are understanding the relation there, right? So that is the reason, that is the reason that entering into the industry is very difficult. People would not want to take a chance. It's not to be mean or talk less about any other industry. It's just that it's not a software patch that you can say like, okay, I can fix it later on. Even the softwares or the firmwares that are running, depending on the end user cases, we have recently seen that some banks software went for a toss and people automatically started spending money or people spending money started getting automatically debited. Okay, so these are also real-time issues. So any places where these kind of critical solutions are used or critical use cases are there, getting into those areas is always difficult. So you think of a day-to-day thing, you think backwards. You will easily realize why it is difficult for you to get into that. Got it? Anyways, coming back to this, thinking logically is very important.
trial,
So keep solving problems. If you're not a person who loves to solve puzzles, you can take up online puzzles. You can play some online games that will keep you thinking. Some games
trial,
are there, some puzzles are there which will enhance your logical thinking. So I keep doing that all the time. So even now, if you see my phone, the kind of
trial,
games I keep installing is where I have to think logically. So that keeps your brain
trial,
active all the time. So that is very important. And then it's just you should understand the chip life cycle before you design anything. So being a design engineer doesn't mean that
trial,
you take a piece of paper, you write a code, or you draw a block diagram and you're done with that. It doesn't work that way. You
trial,
have to give a workable solution to the entire team. You're the start point of the entire chip cycle. So let's assume, let's kind of take building
trial,
blocks and all of this example. So as you design a house, okay? Now you say that I want to. Recently, there was a telco film where he designs
trial,
what do you say, the washroom on the toilet to the wall. He says it looks aesthetically good, but it doesn't mean you like the wall and you use the washroom. Right? That
trial,
is the lesson. So always think about workable solutions. That is the key point or the key takeaway there. So
trial,
anytime you design something, you should understand how will it is it really implementable or not. You can design a lot of
trial,
fancy things, but all those fancy things will not be able to implement in the real time. Okay. So now how will you know how to
trial,
design something which is workable? So you need some guidelines or you need some do's and don'ts for you to design your thing. Okay. That is where this thing comes into picture. Follow your RTL design
trial,
guidelines. Okay. So there are certain set RTL design guidelines given to you
trial,
in terms of how to design a chip or how to bring up a design. So going
trial,
ahead, I'll just give you a quick like example on how this will work. But at this stage, just understand that you should follow the design rule guidelines. Now you have your design basics, you know the building blocks, 18 flip-flop
trial,
bricks. Next, you have a framework how to use those bricks appropriately. Comes your transistor basics. That's the basic thing. If you keep two wires too close, it will form a capacitor,
trial,
or if you connect it in the opposite, it will form a resistive effect. So these are your common basics. These are your common physics laws that you will follow. So all of this
trial,
also needs to be thought of when you're actually doing your design. Okay. So you need not be an expert in the next stages of the chip cycle, but
trial,
you definitely have to understand what happens in the entire chip cycle so that you can provide an optimal solution for
trial,
your design needs. Okay. And then after your basics to create the architecture, I mean, going back to your digital basics, all you have is like your sequential blocks, your combinational blocks,
trial,
meaning your basic logic, gates, and
trial,
flip flops. That's all. Even in the all kinds of flip flops that we use, the flip flop is the basic flip flop that we use on a daily
trial,
basis. So these are the building blocks that you have. Understand based on your coding guidelines, you will know how to use them.
trial,
With that, you will create your. So all these will be based on
trial,
the specification that the client gives you, or whatever you are trying to achieve at the end of the day. That should be your specification based on that is what you can
trial,
design these things. Finally, like I already said, you should always think like an end user
trial,
before you implement your design. Okay. So that way you will know what is the optimal solution, what is that you need to do in a correct way to achieve that. Okay. So I
trial,
hope all of you are following and no bounces here. So I'll just take a minute and if you guys have any questions on this, you're welcome to ask. Don't think it might be a silly question or anything. Anything, just throw it out and
trial,
I'll be happy to answer it for you. No questions?
trial,
Okay. So I hope I get some good design engineers by the end of the session. Okay. So coming to the next thing, what are the required skills at the educational path? So again, the relevant degrees like
trial,
NEC, have to be strong with your physics, medical sciences, and your CS. So these are the few things.
trial,
So these are few subjects that I just pulled randomly from what we study as part of our engineering curriculum. So one is the digital electronics. This is like non-negotiable thing.
trial,
VLSI design is something that you need to understand. Your CMOS technology, Verilog, Backup, and a few of cadence synopsis tools and scripting languages. So
trial,
knowing your scripting language is also very important because on a day-to-day basis, the tools or the environments that we
trial,
use will be mostly Unix based. So that is where knowing some of the scriptings will help you. But anyhow, you have ChatGPT to learn things, so this is something that you will
trial,
eventually do it. So don't worry about it. Okay. So the other key thing that you have to focus on
trial,
is internships and projects. Okay, you might ask me why internships. Now, sitting in a classroom, you have no idea what happens in the real world, in a company, in an industry. So the
trial,
moment you enter an organization, you will be totally clueless as to what should be done. Technically, you might know things, but there are a lot of non-technical things also that you should learn as part of
trial,
pushing yourself into a corporate world. Okay, so getting an internship or spending at least 2 or 3 months under the hands
trial,
of some senior people in the organization is where that will give you an exposure of how to speak with your colleagues, how to interact with your
trial,
customers, how to do your work on a day-to-day basis, how to deliver your work. Because you being a good engineer is not sufficient. You should also be a smart one. You should also be a hardworking one.
trial,
You should also know how to effectively showcase your work when you're in the workplace. So these are the few
trial,
non-technical things that you will learn from internships. Apart from, obviously, you will know how the real-time work happens and what are the things that
trial,
will happen. Okay. So I would suggest and recommend each one of you to try and get some internships, work in the real-time world before you get into the final job. Okay.
trial,
So what are the final? So again, for you to land into internships, the key thing are final year projects or the third year projects that you do, mini projects and final
trial,
projects that you do. So okay, please don't go to Amazbait and buy your projects. Humble request from all of you. Because I also was there at one point. We
trial,
also tried to do the same thing, but eventually we didn't do it. We somehow managed to do our project on our own and we went through it. When you're doing the project, it might feel difficult, but that will actually help
trial,
you a lot. I mean, take it from me. I experienced it, so I'm telling you this. So try to focus more on if you really want to get
trial,
a job in the VLSI industry or be a design engineer or get into any of the companies, try to have more relevant topics rather than just going
trial,
with the flow with what is the trend in the market. Okay, so try to focus more on understanding CPU architectures. It might be a small
trial,
thing, but the way you understand and the way you implement, that is one more thing. Okay, so
trial,
understand, try to get some CPU architecture-based projects or learn about some high-speed protocols like PCIe, Ethernet, DDR. DDR is in the sense like your memory subsystems,
trial,
or some firmware trigger. You already have a hardware, you want to do a firmware trigger, do that as well. So, but try to make it
trial,
very much relevant in terms of what you want to do. Explore a lot of IEEE papers, explore a lot of relevant things, come up with an idea. If you want to go and purchase it, no worries, but purchase the relevant project. Don't buy
trial,
anything random, okay? Then finally, research and master opportunities. This is something I
trial,
truly recommend. I really regret not doing it till date, but
trial,
definitely one day I will definitely do it. Definitely, you should be interested in understanding what is happening in the market, what is the latest researches that are happening. You should always keep updating
trial,
yourself. You might not understand much what is happening around. So, I had a favorite magazine while I was studying electronics for you. I believe it is still there around.
trial,
So we have some small math lab sessions, He'll give some DIY projects to do. He'll give some software to install and
trial,
work on it. So I used to take a lot of interest into that. I'm sure I didn't understand half of what was that being done there. I used to like to follow the steps and do it. But what
trial,
happened is eventually, once you start working, you can correlate back to what all you have learned in the past. So the moment you start correlating with what you have studied or
trial,
what you have read somewhere, you will get more clarity on the real time perspective. So try to do that. Try to like go attend some
trial,
presentations, go present some papers, speak to different engineers, communicate, collaborate, and like go do some socializing with other engineers. Maybe you might be thinking in one
trial,
perspective, the other person might be coming up with a different solution. So these are the different things that will actually slowly build you as a good engineer eventually.
trial,
That logical thinking is definitely required. See, on a day-to-day basis, there are lakhs of engineers graduating. You should always be not just one of them. You should
trial,
always be the chosen one from them. The market is ruthless. Recent times there are a lot of
trial,
layoffs because of a lot of things in the industry. You will not believe they just simply thrown out engineers with 20, 25 years of industry experience without any
trial,
even a little thought. Okay. So there is more nothing like you will have a permanent job. It's not to scare you, it is just to make you aware that whatever you're trying to do or wherever you're trying to get a job in the
trial,
future, always make sure you're up to date. Always try to come up with the latest trends. Always try to learn, keep learning things. You should not think like, okay, I have 15 years of experience, I have 20 years of experience,
trial,
I'm done with it. What who are going to teach me? No, never. You should never have that attitude as an engineer. Till your last working day or till you retire,
trial,
always keep open to new ideas. You might even learn a very basic thing from a 3-year experience or a fresher thing. At the same time, when you're at that level, you will learn a lot of things
trial,
from your seniors. So keep an open mind to learn things and understand things. Okay. So for you to build that kind of mindset, from now onwards, you should always keep learning
trial,
things, studying things, understanding things. Now, I'm not saying go read something that is not interesting you. It can be anything. Whatever you want to achieve, whatever is your end goal, whatever is your passion,
trial,
keep doing research on it, keep doing learning on that, keep understanding a lot of things. So
trial,
I would encourage if you get some research opportunities or you do some master opportunities, please go
trial,
ahead and do that. That will change your perspective in terms of learning things. Okay. And finally, you have a lot of training institutes at the end of the day to go and train yourself. Okay. So more than freshers,
trial,
companies are now interested in hiring training freshers. So whatever is the little skill gap bump that you can get it through the training institute.
trial,
But again, before you go and invest money there, before you go and spend money in these training
trial,
institutes, understand what is your end goal because mind you, you're going to spend good amount of money on these training institutes. And if you try to spend 6 months in these kind of training institutes, you have to
trial,
work very dedicatedly. You have to learn things like anything, ask questions, learn things. Don't feel that what they might think or what people might
trial,
think. You should be literally shameless to ask and learn things. Until you get that attitude, you cannot
trial,
achieve success, at least in our industry. Okay. So these are the few basic things that you should be well aware of.
trial,
Okay. Okay. That's what I was telling. How to prepare for college, online certifications, do some hands-on FPGA projects. We get like
trial,
resource FPGA, the software these days. So you can install them. You can buy an FPGA board, or our college should have FPGA boards. Try to utilize the resources
trial,
that you have. Participate in technical events. That is also very important. There will
trial,
be few technical events that will be conducted for the targeting industry people. Like you have your VLSI yearly conference that happens. Likewise, there are many
trial,
conferences that happen. So there's a lot of technical conferences that happens targeting the industry. day of that this conference, they
trial,
allow students to interact with the industry people. Just go walk in, just understand what the environment is. I'm telling you, you will not understand a damn thing there. Everything will be like alien subjects for you. But
trial,
go there just to inculcate that mindset. Understand things. Even you talk to
trial,
one technical person there, you might get a new perspective, you might get a new direction on what you will have to do. Because I understand at your level you will be very clueless as to what to do, how to choose your career,
trial,
what is it you're interested in. You're like a blank slate at that time. But today you should identify your passion. Unless you identify your passion, you cannot be successful in your career. Okay? So that is something you will get
trial,
only if you go to these kind of technical events. I used to walk into any free
trial,
technical event. I mean, I didn't have this one. So anywhere it is a free technical event, I just used to push myself. No one else was
trial,
doing it. I alone used to go there. I used to talk to people, understand what is happening. I get a new company name. I used to come, try to Google it. We didn't have the internet access. Now you have
trial,
phone. Immediately you can learn about the company. You can learn what they are doing. So that way you will know the industry more and more.
trial,
And then networking through LinkedIn. So don't use LinkedIn like Instagram or what do you say, dating site. Please use it for professional networking.
trial,
So connect with people, understand. So there will be lots of forums on LinkedIn where they keep discussing technical things. You'll have forums for
trial,
technical discussions. You will have forums by a lot of companies. They post, follow all the big companies. That way, if they post anything on their page, you will automatically get to know.
trial,
They will be posting a lot of internship about lots of internships, lot of workshops that they conduct for students. There will be a lot of things on LinkedIn that you can actually materialize. There will be people who will be just randomly
trial,
posting some technical sessions that you can access free of cost. People will be just conducting some online sessions for free of cost for students and freshers. So there will be a lot of these things. Just
trial,
based on your interest, keep following those pages, keep randomly adding people, whomever you find interesting. That way, once you start following these people, you will get more and more insights to the industry. See, now you have all these accesses.
trial,
Try to use it to understand things. And it's finally is like
trial,
building a perfect technical portfolio. Okay, the term might sound very
trial,
heavy or like fancy item or something. Simple thing, how to present yourself as a good engineer. Because I would say go use ChatGPT, give all your data, and it will come up with a nice
trial,
something for yourself. So you have AI tools, you have a lot of these access tools. Don't just use them for fun, use them for your technical growth as well. So that will build out a lot of options for you. You can choose
trial,
profile that you find is relevant for your work, and that way you can create your portfolio when you're creating
trial,
your resume, when you're creating your LinkedIn profile. Make it interesting. Make it a bit more relevant
trial,
for the recruiters to be able to approach rather than having that typical
trial,
one-liners or typical taglines that everyone use. Okay, so that
trial,
is how you can kind of enhance your portfolio and you can start preparing it. For you to build a portfolio, you should have done some at least some basic research. You should have done some at least
trial,
one or two hands-on projects. You should know technically things that is when you can actually go ahead and build your technical portfolio. Okay, so that is what is how to prepare for college. Okay, now the very interesting part, the salary trends and
trial,
growth opportunities. So this is where I'm going to attract you guys. So anyone can tell me what would be the basic salary of a VLSI engineer or a semiconductor engineer?
trial,
Let's say you have 3 years of experience. How much do you think you can earn per annum?
trial,
1 crore per annum. Okay, you will end up getting 1 crore,
trial,
but it takes a lot of time and effort for it. For a 3 years engineer, let's go basic. For a 3 years engineer, true, very true. So So you will get
trial,
anywhere between 5x to 6x of your experience. That is the current market trend that is happening. So, but whereas you compare with the software guy, he would not earn that much.
trial,
The moment you hit a mark of like 18 years, 20 years, you will definitely end up getting 1 CR as your salary.
trial,
Not getting it, don't worry. So, so that is the kind of
trial,
that you can imagine after you have like 6, 7 years of your experience, or by the time you are like 30, 35 years of your age, you will be in a position where you will not think of money. You can,
trial,
on the flip side of it, you can support your family, you can be settled down, and you can retire at an early age with no financial
trial,
commitments or no financial stress. Okay, so, but the initial efforts that you have to put to get that is also huge. For you to sustain in the industry, keep growing also is equally important.
trial,
So from 18, the journey between getting a 15 lakh package to a 1 CR package is huge. Mind you, it is really huge. You have to put in lots and lots of efforts. You have to be the
trial,
best in the industry. You have to be up to date with the trends. You should know how to quickly, smartly solve certain problems. You should be an independent engineer. You have to think for yourself. You will not have
trial,
any people to sit and teach you there. The first day you get into the job, they'll be like, do this, do that. They'll not
trial,
tell you how to do it, where to do it, what is the start point. You have to just go figure it out.
trial,
This is the point where all these things will help you. So, whatever you do
trial,
in college, every small thing, like let's say you are doing a project for yourself, then you will learn how to get things for yourself, how
trial,
to manage without the required tools, what are the workarounds or the jugaads that you can do to do things. So, all these smartness or
trial,
different smartness that you use in your initial days of your career and your college life is what will help you down the line. That is what distinguishes you from
trial,
a regular engineer to a smart engineer. Got it? So that is the reason you have to do all of these things, you like it or not. But there is no compulsion, or I'm not saying that you definitely have to do it or this is how you have to do it. These are the things
trial,
that I followed which work for me well. And I know a few of my friends who have done the same
trial,
things and they have in very good positions these years. So these are some things that will definitely help you. These are proven solutions. And again, you have to be
trial,
really passionate, you have to be really patient to get that. I mean, initial years, till you get the experience of like 4 or 5 years of your career, you should not think about money. You should not think about what is going on, how much
trial,
work you're putting in. You have to work hard for like 18 to 20 hours per day. Learn things. That is when you will go from 15
trial,
hours to 1 year. Okay. So, what is the career
trial,
growth or the career ladder will look like? So, you join as an engineer or a junior engineer, senior engineer, tech lead, tech manager, associate
trial,
director, and director. So, I'm somewhere between the tech manager. So, hopefully, I'll become an associate director and director soon. So, that
trial,
is where I'm there. And what are the global opportunities? Definitely, we do have a lot of companies hiring outside India, but within India itself, we have lots of startups. We have a lot of companies who are ready to give jobs. The
trial,
only thing is that you have to be good enough for them to hire you. So that is the hard work that you have to put into. It is not easy. You have to have a
trial,
lot of patience and a lot of passion to do it. So if you really decide that you want to be in this industry, you have to buckle up and start working from today. Okay? Yeah. Again, like as I mentioned earlier,
trial,
so these are the challenges and the future trends that you can see. So the challenges is that we have the skill gap. Air revolution is one of the challenges. The changing consumer expectations. It's like daily
trial,
everyone wants like faster chips, power efficient chips, smaller chips. You need smaller phones, sleeker phones. You need
trial,
high speed gaming boxes. You want faster cars. You want automated cars. You want to just give a voice command and everything
trial,
should come out within a minute. For us to design those kind of complex chips, it is really
trial,
difficult. So the market turnaround is what we call TAT, turnaround time. So from the spec to getting a chip, it's called a TAT. Initially, the TAT used to be like 2 years, 3 years, but these days it is 3 to 6 months.
trial,
Within 6 months, you are not coming up with your next version of the chip, you are out of the market. That
trial,
brutal is the industry, and that brutal is the competition in the industry. Okay. And what are the future trends that you can look for
trial,
when you graduate? These are the industries that will meet the boom. AI industry, obviously, EV, power management, avionics, medical, banking. These are the sectors where you can see a lot of automation happening. Now, you can ask
trial,
me, how is AI booming industry? Okay. The interesting fact is that the AI capabilities that you use on your devices need AI
trial,
accelerators and AI supporting hardware in the background to design that. So it's a kind of analysis that we are designing AI machines to kill our jobs.
trial,
Okay, jokes apart. So it needs a lot of high-speed computations. So you would have heard of CPUs, GPUs.
trial,
Latest thing that we are hearing about is NPUs, neural processing units. So what are these neural processing units? They do a lot of AI computation.
trial,
They run a lot of math behind them to kind of compute and analyze the data
trial,
inputs that we give to these AI engines to come up with better solutions. So we need hardware accelerators. We need chips that support these kind of computations and neural networks. So that is where
trial,
AI also comes into picture. And EVs, again, we are moving towards
trial,
fuel efficient solutions for automobiles. So there again, you need a lot of power management systems because the moment the battery comes into picture, there will be a lot of digitalization that happens even in your engine circuitry and a lot of these things. So it is like mechanics plus
trial,
electricals combined. So that is one more interesting industry to explore. And then
trial,
management. So power management is a very broad umbrella that will fit into all the industries, all the chips that you are working on. And next comes your avionics and your medicals. Okay. The Indian
trial,
semiconductor ecosystem and growth, I've been talking from the beginning itself. So we do have a lot of fabless companies that are already there and that are coming up. So recently I got an
trial,
opportunity to work with a startup where we designed the IoT-based solution that was immediately sold off to both companies
trial,
actually. So the chip that we built within an year, it got into production and it went into an end user and people are using it. So that kind of gives you a very
trial,
like a good feeling that something that you work on is you being used in the real time. So as I was saying, the TAT has reduced. So whatever you're designing now is something
trial,
that people are going to use immediately. Just to give you a quick example, pretty much many of your
trial,
Androids would have a chip or a design by Qualcomm called Snapdragon, correct? So any
trial,
idea when the first Snapdragon chip was designed? So the first Snapdragon chip came out in 2010.
trial,
People are still using that after 15 years, 16 years. So that is the kind of R&D
trial,
technology advanced thinking that we do in the industry. But yeah, now things have changed. We just think for immediate solutions, or we are just thinking for
trial,
solutions for the next 5 years. But initially, the industry used to think way ahead. So even before the first 4G chip came into picture,
trial,
Qualcomm started designing that work almost like 5, 6 years back itself. So by the time the first 4G chip came
trial,
out, we had already finished designing the next chip. We had tested it and we had done a lot of
trial,
R&D on that. And we also started working on the next versions of it. Likewise, in all the industries, that is how
trial,
advanced we keep thinking in terms of the designs and the technology. But now that has come to a lesser period, as I was saying, that the TAT has reduced. But that is how
trial,
we have to think ahead of providing the solutions. Okay, so that is to give you an insight on the challenges and the future plans and things like that.
trial,
Okay, now I leave it to you. Any questions, anything that you would like to ask me before I go into much more boring stuff? You are welcome to ask.
trial,
Okay, to give you a very funny answer, I realized that I didn't learn anything from the college. Sir,
trial,
he would say I was one of the good students in the college, but no, seriously, after I graduated, the first thing I did was like, I felt to myself that
trial,
I'm ready for the industry. They just have to like, come on, Ramya, I'll give you a job, sit at work. That confidence is what I had. So I had that
trial,
the first time I took my first job interview. So I had to go sit down, write
trial,
written test. Mind you, I'll not say I was always a topper, but I was always a consistent student from my childhood. Failing was never an option for me. The moment I saw the paper, I literally cried there,
trial,
thinking that I'm going to fail this exam. For me, stage failing an exam was the biggest insult for my life. Okay. So then I realized that, then I understood. Sir used to literally shout at us,
trial,
read the basics, understand the things, practice it, practice it. We used to do it, but we never had the seriousness of how to do it or when to do
trial,
it. So then I went back. That's where I did a course actually. I did a mistake of
trial,
doing a master's course, but I did a diploma course to understand the basics. Like it was not a training institute; it was a diploma course by University of Pune. So I went and did my PG diploma for 6 months. Those 6 months
trial,
is where I went back, I learned my basics thoroughly. The next year I came back, I went to the same company, I cracked the question paper, I got the job offer in hand. That is where I felt, okay, now I've learned things. So that is why I was stressing you a lot. Learn the
trial,
basics because we think that we know things. Because in college, all we try to do is get good marks, or our thinking will be different from
trial,
that perspective. So we would not relate to how to give a solution. Let's say, for example, all of you would have read about microprocessor. Now, if I tell you, take the microprocessor,
trial,
of the microprocessor for it to become an actor. Can any one of you do it? It's a very simple solution, but we cannot do it because we never think from that perspective. But it is there
trial,
in front of us in the textbook. You know microprocessor architecture, you know what are the boards which will have to be connected to make it happen.
trial,
But we never think from that perspective. You got it? So that is the kind of thinking that we have to build. Now all of us get about a grade. Now design a full adder using just two adders. Can you do it?
trial,
No. That's not a real problem though. But now I say
trial,
full adder, somehow you will do a design a full adder. But that's not how they will ask the questions when you go to the real time world. When you want to go, even for your internship, when you go, you write an
trial,
exam. Because till you are a experienced person, all your first initial job interviews will have written exams to it. So all these written exams,
trial,
they will not ask you how to write a Verilog code or how to solve a problem. No, that is not what they will
trial,
ask. They'll ask you comfort your distance and they'll ask the real-time implementation of your digital blocks. They'll say, okay, I give you a flip-flop.
trial,
Draw the flip-flop. How many of you can do it? You cannot do it. You cannot do it. So I will know a basic
trial,
diagram of flip-flop. It is very easy. You have a table. You just have to know how to convert it into a timing diagram. It's there in your textbook. If you want to open your textbook, you will read the flip-flop definition. You will have
trial,
truth table, and below that they show it in timing representation. So that timing representation is what you have to understand. The moment you understand that
trial,
representation, you designing a chip is like very easy. So the implications of what we are learning, how we are applying on that is where we will lack. So that skill gap is something that I
trial,
had a lot in me. Even though I graduated with a distinction, I got a fancy certificate, everything. I felt I was more
trial,
to get that certificate because I didn't learn anything is what I felt. See, again, perception, nothing to do with anyone there because I felt I didn't spend my energy in understanding those things.
trial,
Got to know that only when I know how what is the expectation from the industry. Got it? That is what you should always know what are the expectations from you. Once you know that, you will automatically
trial,
yeah. Okay. So what I would say is go attend for some internship interviews. You need not get selected. Get happy,
trial,
but you will know what is expected from you. Because otherwise, no one will sit and tell you what is expected from you.
trial,
Learn your basics, get good marks, we will take you. You will not take you. You also not hire you if you tell me that.
trial,
Because that will not work in the industry. Got it? So your real time implication, how you are thinking logically, you might not be 100% back on with your solution. But the approach that you are taking itself defines your
trial,
approach here. So even when I'm taking interviews on a day-to-day basis for one, the way I try to analyze the engineer is that how is that they are approaching? How is that they are coming up with a solution from the ground basis?
trial,
So that is the approach that are they taking? Are they going in the right direction? Rest can be learned over the job. It's just that your thinking and mindset is something that you have to shape.
trial,
Okay, so that is the right action that you will need. So that is the skill gap that you have to cover for yourself. Okay, I hope I answered your question. Any other questions?
trial, trial,
Okay, so I will tell you a very, I would say like a blunt answer to this. It is not always necessary that you have to be a master's graduate, but I think that will be a good
trial,
start point for your resume to get shortlisted. Let's say for a job, there will be 100 people who are applying. Now, as a recruiter, how will I filter those
trial,
100 profiles? So I need a benchmarking for that. So I will say,
trial, trial,
so what I was saying is that so just to qualify your profile, they might be taking
trial,
Intech as a benchmark, again with a GPA of so and so as a benchmark,
trial,
or trained freshers as a benchmark. So it is not always necessary to pursue an Intech, but if you have an opportunity and you are really interested in pursuing an Intech, please go ahead and do it. Because that will be an additional layer for your profile to get
trial,
shortlisted quickly. And again, taking a real-time training will also help you. I mean, there are, let's say, for example, you say like, I mean, if I'm being very practical, you say like, see, I cannot financially afford
trial,
me get into MTech, spend another 2 hours on education, not help my parents financially, then I can totally understand.
trial,
You can be a graduate, get yourself trained on something, get into a job. A lot of companies
trial,
have integrated MTech programs within their organizations. Also, including our company, they
trial,
partners with BITS, IIT, Triple IT, Hyderabad kind of institute, where you can still keep working and get a master's graduate. That will eventually help your salary packages and
trial,
other things. So having a master's degree is always something that I would support, but it depends on your current situation and your interest. If you want to pursue it immediately after
trial,
a break or while doing your job, that is something that you can make a personal choice. Okay. Okay. Any other questions?
trial,
No questions. Okay. Nice. Then I'll go to another boring PPT.
trial,
So this PPT itself,
trial, trial,
yeah.
trial,
Okay. So as a fresher, the first and foremost basic thing is your
trial,
attitude. That counts a lot in the industry when you go to get a job. Okay. So hiring a person is a total different thing actually. So the way they hire a person in the
trial,
real time world is totally different than what we expect. See, because during our campus drives or during our campus interviews, many of the software companies they just come hire you
trial,
based on your marks and the attitude that you have done, and then they take you into Bharat. So the reason they do that is because the kind of projects or the volume of work that they have, they will train you as a good and they
trial,
will segregate you. You will go and work in the real time. But our industry is slightly different from that perspective because ours is a very close community, I would say. Let's say, for example, you work for 5 years in the industry,
trial,
pretty much every other company you will have someone or the other as reference. Okay? Some of your managers would have moved from one company to other. The
trial,
colleague sitting next to you would have gone from this company to other company. So after 5 years, it so happens that let's say you have been
trial,
in a company for 5 years, sixth year you want to change your company. So at that time, only reference works. So they will, whoever is trying to hire you, will call up your previous manager or the company
trial,
that you worked in, and they try to get a feedback about you, technically, not technically. Technically, you might be brilliant. Sometimes they say, "अरे यार तो पहले सोच रहा बाबू, अच्छा डरना आता पहले स्टार्ट हो तो." Okay.
trial,
Technically, or also that manager will be like, "I don't need this kind of a person with me." Okay. So the first and foremost thing is your attitude. You have to be with right positive attitude.
trial,
Global ఎంత తిట్టుకున్నా బయట మాత్రం క్లియర్ గా ఉంటారు. You have to maintain that relations. So for that is the first thing that they
trial,
see in you. The moment you enter the interview room or the moment you start interacting with the person, how you are presenting yourself. The
trial,
second thing is the confidence with which you speak. I understand you will have a lot of lecture. It's been 16
trial,
years I'm working in the industry. Even today you ask me to go for an interview. Local let's say from the tension I go to them.
trial,
Because I have that fear in me. But again, it's how you not show that fear and speak confidently. The third and very important thing is
trial,
projects. Because you will not have any other technical background here as such. So it is your project that will give a direction for the
trial,
interviewer to ask you the relevant questions. Otherwise, he can ask, he or she can ask you from anything that you have studied in your engineering. So your project
trial,
or the mini project or the final project that you do, that you put on your resume or the papers that you have presented in the past, whatever the technical things that you put on your resume, will give you the will give you the
trial,
direction to ask you the questions. Now all the questions will be around it. Let's say for example you went and you presented a paper in some college. So it has
trial,
that okay, AI trends, blah blah blah. You found it very fancy online. You picked it up. You went and you presented. But what is equally important is you understand what is
trial,
there. Even if you have not done it really, and you have just put it for the sake of keeping it also, you should be able to speak about it. The
trial,
moment you start explaining about it, we will know whether you have done it or not. Got it? So because even we loved it the same way you guys did 10, 15 years back. So we would understand that. So never
trial,
be bluff. Don't try to bluff anywhere. Be as honest as possible. You know something, you know. You don't know something, you don't know. But be very careful on what you're putting in
trial,
in terms of your technical skills. Because that is where you will be asked for. If you don't
trial,
deliver their expectations or don't answer any relevant questions to those technical things that you have kept in your resume, you're gone there.
trial,
At the end of the day, your willingness and passion to learn things. Sometimes what happens is that, let's say you answer a question, the opposite person wanted you to start
trial,
that you are wrong. How will you present it? You should not start arguing with them there saying that no, no, what you're saying is wrong. What I'm saying is correct. So there is a polite way to put it also.
trial,
The reading that I have done, or these are the references that I took. My
trial,
understanding about this topic is this. If you're saying the otherwise, I would like to understand your perspective on what basis you're talking these facts. I would like to understand.
trial,
That's the polite way of main correct without. Okay? So ask ChatGPT tell
trial,
what is the right way of putting it and what is the wrong way of putting it. Anyways, so these are the basic key factors
trial,
everyone will look for in your interview. So be very mindful about what you are putting in your resume for the initial anytime, even after 10 years of experience also. These are the key factors that you should always keep in mind. But it is more about
trial,
your passion, what is it you are willing to learn, and what is the basics that you hold. So these are the
trial,
basic things that we will check with you. Because we would not have any other things to ask you because we know that you don't have that industry exposure yet. So these are the few things that we will
trial,
grade you up. Okay. Any other questions? Yeah.
trial,
Yeah.
trial,
Okay. So
trial,
to answer it in a very simple way, the approach of teaching or the approach of those students these are 90s or these kind of
trial,
institutes will be a bit different than the regular institutes because that's the kind of exposure
trial,
that they keep getting. So just to give you a quick example, recently we read in news that there was a processor called Shakti, India's first processor that was built
trial,
by IIT Chennai, this, that, and all. There were a lot of news. So what happens is that since these institutes are there in the
trial,
like education system from ages, they are known to produce premium engineers. There are a lot of institutes like CNAC, a lot of startups. What they do is they go collaborate with these
trial,
colleges and they set up incubation centers. They give them real life projects to work on. Got it. So in a way, they are utilizing
trial,
engineers to train them while they are still graduates. They are taking off the top training from them. Okay, so that is where by the time you graduate, you are already a workable engineer. I need not spend my time to teach you things.
trial,
The moment you come into the industry, you will be ready to give back what you have learned. Right? So that is where. So you are already 10 steps ahead than me.
trial,
Automatically, the salary will also be there. See, at the end of the day, getting more money is also not the key thing here, okay? Because, okay, I'll say like to be a smart engineer, I mean, that is also one more thing you should always keep in
trial,
mind. You should never jump to a job and say like you'll get 15 lakhs, 20 lakhs immediately. Because tomorrow if they have to throw you out,
trial,
you'll be the first person to throw you out because I can hire two more engineers with that salary. So at that time, when the time comes of throwing out, they will talk in terms of money, not with skill and experience.
trial,
Okay? So anytime, anywhere you go to a job, in any industry, always look for a package where you are there in that sweet spot, where you are not highlighted too much, still you are getting the money for your package.
trial,
Okay? So that is also a key thing when that you have to keep mindfully when you're switching between the jobs. But as a fresher, it is purely your luck and what kind of companies you will get into. My first salary was
trial,
okay. So I didn't get any opportunities at that time to get into big companies. So I had to start from the scratch.
trial,
So few will get that start point very early. Few will have to struggle a bit to get that start point. So that's where you see the difference.
trial,
Because nowadays, pretty much even including our college, we are trying to teach the students on the tools and what
trial,
things get you that industry exposure. So that is why you can see a lot of your seniors getting very good packages as they are
trial,
graduating. So the more skilled you are, the more you are industry ready, the more money you will get. Simple as that. If they have to just take you and train you, they will recover that training cost from your salary. Because at the end of the day, you are not
trial,
taking you are just a resource in terms of money. Okay? For you, it is a salary and you are livelihood. For them,
trial,
it is like profit and loss statement. So that is how they treat you. I mean, it might seem very pathetic to hear, but that's the reality
trial,
we all have to accept.
trial,
So suppose you want, like we want to invite you for like industry collaboration. So what are the qualities you see in students and what do you expect from those
trial,
to like reach a high level such that we can have like industry and like this collaboration so we can train. So if I really have to set up an incubation center or if I really want to train my
trial,
engineers, all I say is that I want engineers to be really serious about what they're doing, put in all their effort, because they want to
trial,
learn. Rest I can teach you guys. So unless you have the willingness to follow what we are saying to your team, no worries. So that is the main thing. And next is your logical thinking. You should have logical
trial,
thinking for yourself to be that kind of a design engineer. See, now I am talking more in terms of being a design engineer. But in general, to get into the industry, you should have the
trial,
basics. You should have the passion to really put in that effort. So if you show us that
trial,
passion that yeah, I'm ready to learn, you accept that these things are these things. The more transparent you are, the more passionate you are, the more willing you are to learn things. Definitely we can teach you.
trial,
If you are just talking for the sake of money, okay, with that also, but again, sit and learn that.
trial,
Okay, but your end goal should be to learn what we are trying to teach you. So that you to grasp things, understand things,
trial,
learn things, put in that effort is what counts a lot at this stage.
trial,
Anything else? Okay, so I will stop. I will break here.
trial,
Okay, we have a quick break time. So once we are back, I will go you with more detailed technical stuff,
trial,
what I do on a day-to-day basis. And yeah, then we can talk more. Okay. Thank you guys.
trial,
Requesting all the participants, please have your participant create and after a couple of minutes, we will join in the session. Thank you.
trial. trial,
So now I would be walking you through some of
trial,
real-time implementations and how actually a day-to-day RTL engineer does his work in terms of uh, the
trial,
designing. Okay. Okay. So as you can see, this term PPA. So this is a very key driving
trial,
factor for us to design all our chips. PPA stands for power, performance, and area. So these are the three key driving factors that we try to achieve
trial,
as part of our designs and every stage of the implementation till the end of the chip cycle. Okay. So PPA plays a very key role in all kinds of
trial,
decision making in terms of how the size of the chip should be, what is the
trial,
optimal design that you are supposed to create, and what is the best possible solution to achieve this PPA target that we have set for our design.
trial,
So going ahead, I'll just quickly
trial,
uh, give you a realistic example in terms of the last project that we have done. So the average team experience that we had is 6 years. So we had a team of five design
trial,
engineers that we were working, and the average team experience that we had for that particular project was 6 years. Okay.
trial,
So what do you mean by average experience? Let's say you have a team of five engineers. One person would be a senior lead with like 15 years or 10 to 15 years
trial,
experience. The next will be a sub lead with like 8 to 10 years experience. Then you'll have a bunch of juniors with like 3 to 5 years of experience. So if you average out
trial,
the entire team's experience, it brings you to 6 years. Okay. So why is this metric very important for us in the industry? Is because it defines that what is the team
trial,
strength or the experience strength that we are bringing into this project, the real-time experience strength that we are bringing into the project. Okay. Now let's walk through the core competencies that our engineers had or should
trial,
possess or should have for us to execute the projects in the real time. Okay. The
trial,
first thing is the coding experience, either Verilog or VHDL. VHDL is slightly outdated now. Pretty much only the defense related projects
trial,
have the VHDL still going on for their day-to-day projects, whereas Verilog HDL and System Verilog are the current HDL languages that everyone is using
trial,
these days. Okay. Now, just to give you a brief, how is a coding language in
trial,
our industry different from a coding language that we use in a software environment? So if you look here, I'm saying Verilog HDL. Okay.
trial,
HDL means hardware descriptive language. So in software, for you to achieve a solution or to
trial,
write something, let's say you want to swap two numbers. So what you do is
trial,
you just write a code to swap two numbers. You say A is equal to B, B is equal to C, blah blah blah, and you achieve the code to swap two numbers. Whereas if you want to
trial,
do the same thing for a hardware, let's say for example, I want to design a hardware that can swap two numbers, then I cannot write the code in such a way. I cannot write the code like I do it in the software.
trial,
So in Verilog or in our industry, the coding that we write is
trial,
always keeping the hardware in the mind. Okay. So let's say I want to achieve swapping of two numbers, then I will create a
trial,
flowchart, I will create a block diagram for it, and I will mimic that block diagram using my Verilog
trial,
coding. Okay. It is not the other way around. Whatever you write as a code should not turn into a hardware. Whatever that hardware you want to come at the end, based on that, you have to write your Verilog code.
trial,
Okay, that is how you have to think as a designer, and that is how you have to write your Verilog coding. Okay, if you have to design an
trial,
half adder, full adder, think of the circuit of the half adder, full adder, draw the circuit,
trial,
understand the output. From that is what you have to write your Verilog coding. Okay, I'll tell you the
trial,
reason why we have to do it that way going forward. Okay, the next is that SOC RTL integration, and then the
trial,
flowcharts, the synthesis. So these are the basic, then the understanding of DFT architecture, ATPG coverage analysis, and then development of memory behavioral
trial,
models, spice models, validations, lot of these things. Okay. Now this might all sound very Greek and Latin at this stage, like what is what. So I would just like to take an example.
trial,
It's here. So I would like to draw your attention to the board for a minute. Let's say, for example, I have a system. Okay. So SOC is
trial,
nothing but system on chip. So basically, you are trying to build an entire system that
trial,
can work on its own on a chip. That is what is called as SOC. Okay.
trial,
This is nothing but system on chip. Now, how do I achieve this? Let's say, for example,
trial,
I want to design one SOC. Now, I should understand the specifications for it in terms of what does my chip has
trial,
to do. So, based on these specifications, I say I will divide my logic into
trial,
4 parts, saying that I need an ALU, I need a CPU, I need a memory like an SRAM, and then I need
trial,
something to connect this, which I call it as a NOC, or a NOC nothing but it's a network or the interconnect on the chip. That's all. Like you have to write
trial,
everything down, right? So for that you need one NOC. So based on my requirements or the specifications, I will say that at a broader level, I
trial,
need these 4 blocks to achieve my end goal. Let's say, for example, you want to build a how do I put a vending machine. Okay, so for you to write that logic behind
trial,
that vending machine, what is the thing? You put a coin, you select the item, and then it will come out. But there is some circuit behind it which is helping you to do all of these
trial,
things. So what are my inputs here? uh, Pressing the button, inserting the money.
trial,
These are my 2 inputs and the item. So these are my 3 inputs. So for these 3 inputs, what are the possible output combinations 2 par 3? That is a standard. So based on all your
trial,
specifications, you can come up with 2 par n outputs or solutions.
trial,
Okay. But in this 2 par n, you will not have everything as a valid solution. So you as a design engineer,
trial,
you will start the elimination process of out of these 2 par n outputs, you will slowly start eliminating the
trial,
invalid outputs or unachievable outputs based on implementation, based on logic. Okay. Now let's say, for example, when I say I have an
trial,
input as coins. Now you can ask me, can I insert 2 coins? Can I insert 3 coins? Or it is just like one
trial,
coin that is insertable, or I can insert a note and will it give me a change? All these are possibilities, correct? But in vending machines, will all of these happen? No. It will say insert 5 rupee coin, 10 rupee coin. That's all.
trial,
Correct? So here, out of all the possibilities, out of all the 2 par n inputs or all the 2 par n
trial,
combinations that I can give it, I am choosing only 2, which is a subset. So these 2 are my valid inputs. Now I will build a circuit only targeting these 2 valid inputs.
trial,
Anything apart from these 2 inputs is given to my system, I will not accept it simply. That becomes your
trial,
specification document. Okay.
trial,
So once you get the inputs from the customer, you will see what are all the outputs that can come from it, and you will go back to the customer,
trial,
discuss on what are the valid outputs. From that is what you create your specification document. Okay, so this is like a
trial,
golden thing. Everything needs to be documented in this, and this is the first job for you as a design engineer, to understand how to come up with a specification document. Okay, this
trial,
level of creating specification document will be done once you have a lot of experience, like after 10-15 years of experience. Okay, but as a design engineer, this will be your first job,
trial,
to create a specification or understand what are the how to translate the expectation from the customer to a real workable solution. So that is a simple thing.
trial,
Customer asks something, you will create a specification document telling that this is the real time workable solution
trial,
for all the requests that you have made. Okay, so this is more like a blueprint for your house. Okay,
trial,
so this is like the key document for you. From this is where your starting point. All the teams in the entire chip life cycle will always refer back and do your
trial,
work. Okay, so now once the specification document is there, from there, so again from the
trial,
specification document, you will come up with something called as a architecture diagram. Okay, now you ask me, let's say I want
trial,
to design a FIFO. How can I do it in these steps? So you know what a FIFO does, correct? First in, first out. Now it can be a synchronous FIFO, it can be an asynchronous FIFO.
trial,
It can operate at two different clocks, it can operate on one clock. The size of the FIFO can
trial,
vary. The inputs coming to the FIFO will be like, I'll have 10 inputs at a time, and then the data will not come for
trial,
another 2 cycles. Then again from the third cycle, again 10 inputs will come. So these are the inputs, or these are the
trial,
specifications, or these are the requirements that I'm giving as a client
trial,
to you, saying that design me a FIFO with blah 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 these things. Now from that, you have to come up with
trial,
something called as a real workable solution. So this can be a specification list that you can just
trial,
jot down, saying that these are my workable solution for what problem you have given, correct? From that you can
trial,
either come to an architecture diagram depending on the complexity. It's just a FIFO. So for that, you can just come up with a flowchart. Okay, so that flowchart becomes your blueprint
trial,
or your specification document. Okay, from that flowchart or from that specification document, you will come up thinking how to design it. Okay, what are
trial,
the real hardware components that should go into for you to achieve that particular flowchart or specification document. Okay, so this is what is
trial,
called a architecture diagram. So this is a very basic architecture diagram that I'm saying. So CPU is nothing but your master, and these are all your slaves. So you take any SoC,
trial,
thumb rule, you'll have a one or multiple masters, and you'll have bunch of slaves. Master is
trial,
something that will drive or give you the commands, and slaves are some things which will take those commands or instructions from the master and do the job for you. Simple. Okay, now what does this
trial,
uh, SoC RTL integration mean? So what we do is, you cannot design everything at once. Okay, now you have an architecture diagram, then you do something called as a micro architecture. You divide this further down.
trial,
So I will take out ALU as one IP. So I call it as an independent design.
trial,
SRAM as one IP, NOC as one IP, and CPU as one IP. So there will be two or
trial, 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 trial,
It means it's a design flaw. You have you have designed in such a way that
trial,
you press something, something is coming out, but that is not the end goal, correct? So the end goal is
trial,
what you press should come out, correct? So it means your design is structurally
trial,
correct. Structurally, you press something, something is coming out. So structurally, your
trial,
design is correct, but functionally, it is not correct because it is not giving you the desired output, correct?
trial,
So every time at every stage, your design will be tested or
trial,
qualified both structurally and functionally. Got it? So structure wise, are you following the design coding guidelines? That is one check that we do. And functionally, is it actually achieving what you have
trial,
defined in your blueprint or your specification document? That is one more check that we do. Okay. Now, as design engineers, what we do is we do the structural checks on our
trial,
design because our design eventually will go into backend teams where your
trial,
coding or whatever the hardware descriptive language code that you have written will eventually be
trial,
converted into gates or real time design. Okay. So when this real time design conversion happens, your design undergoes lots of transformations. So at every point, you should make
trial,
sure that you're structurally checking your design against this, correct? It should not happen that
trial,
you, let's say, uh, if we take the analogous example of building a house, let's say you have an architecture, you say like, I want a 3 BHK. But you should also verify if that 3 BHK is as per
trial,
Vastu and where you have kept the bathroom, where you have kept the bedroom and where you have kept the puja room, right? It should not happen that that fellow comes and say, you asked for a 3 BHK, I built 3 rooms in a row and given it to you.
trial,
It doesn't work that way, correct? So structurally at every given point of time, you keep verifying if your design is intact and still the same, matching to what you intended it to be.
trial,
Okay. So as a design engineer, it is your responsibility to do these front end flow checks to make sure that whatever design you are implementing is structurally still intact
trial,
even after it undergoes lots of transformations. Okay. Now, once you do these front end flow checks, you do something called as
trial,
synthesis. Okay, so what is synthesis? Basically, whatever the hardware descriptive
trial,
language that you write is now actually getting converted into hardware. Okay, now remember the first point that I said, that you should always keep the hardware in mind and write your Verilog code.
trial,
That is what will give you the best results for your synthesis. Okay, let's say for example, uh, if you guys are studying Verilog, you know Verilog. Okay, so you have
trial,
something called as an always block, correct? So you have two types of always blocks that you can write. One is a combinational always block and one is a sequential always block
trial,
that you write, correct? Now, when you're writing a sequential always block, the moment you write an if
trial,
else condition, it will be translated either into a priority logic or into a muxing logic. And now if you implement the same if else
trial,
statements with sequential logic to it, then it will either translate into a flop or a latch. Okay. So these are some basic coding
Trial.
guidelines. If you remember previously, I was talking about RTL coding guidelines. So using those RTL coding guidelines and your design basics is where you can actually form your optimized Verilog code. Okay, because
Trial.
the reason we have to do all this Rama and Mahabharata is because whatever the synthesis tools that we are using,
Trial.
see, it is practically impossible for you to sit and
Trial.
draw gates for your circuit or for your implementation, because the kind of designs we are handling are huge. Okay, so for that it is practically impossible for any human to sit and design
Trial.
the circuit at the circuit level. That is why we are going to write it in the form of a human readable
Trial.
format that will be translated into gates real time. Okay, so this synthesis is done. This process of synthesis is what converts your actual Verilog code into a gate level netlist is what we call. Okay, so this
Trial.
conversion happens through few tools which are again software. Okay, so these software tools will be fed with predefined programs or predefined way of writing the codes following the coding guidelines.
Trial.
So the moment, how will the tool know? Otherwise, it has to translate into a AND gate or adder or a sequential circuit or a flip flop or a, what do you say, like a
Trial.
counter or a synchronizer. How will the tool know? The tool will not know, right? It is
Trial.
because we have designed the software in such a way that the moment it sees a way of coding style, it knows that this is nothing but a mux implementation, this is nothing but a flop implementation, this is
Trial.
nothing but a latch implementation, this is nothing but a FSM, this is nothing but a synchronous
Trial.
circuit. So that is how we have designed these tools. Okay, so that is why it is very important for you to follow the coding
Trial.
guidelines, understand the design, and then write your hardware descriptive language. That way you are making sure that your design is
Trial.
properly getting translated into the intended hardware. Okay, so that is what happens in the synthesis stage. So as a
Trial.
synthesis engineer, you have to follow all these things. Okay, you have to give it certain constraints, you have to give your RTL as your input,
Trial.
then you have to optimize your design. So the tool will do a lot of optimizations there to reduce the area, because sometimes you would have written some
Trial.
redundant logic unknowingly, or sometimes there will be, in the real time world, half of the time it will be like there are
Trial.
already some uh, blocks that were used in the previous chips or previous versions of the design. You will just take it and reuse it, or you will take it and modify it for your design needs. Sometimes you will not do from the scratch
Trial.
development. So for all of these things, the tool by default will do some optimizations to remove the redundant logics which is not required, or which is just dead logic is what we call. Because if that goes into the chip, it is of no use, but it is occupying the area,
Trial.
it is consuming the power. That will reduce your PPA that we were talking in the starting, correct? So that is how you
Trial.
have to keep in mind all of these things, and you will reach till the synthesis stage. So once the synthesis is done, your job as designer is done. Now this will be passed on to the backend team, who will
Trial.
actually do the place and route, do the clock tree structure, do the reset structure,
Trial.
do all of those things, and they actually place your design on a board. So I'm pretty sure you would have used a lot of these layout tools for cadence and all as part of your course or
Trial.
additional activities that you're doing. So that is where, after this thing from the designer is given to them, all of these things happen. Okay, now, so till
Trial.
here it is fine, or it is too much, you want me to repeat something? Okay, okay, now
Trial.
going ahead. So this is how a day-to-day designer's life will be revolving around understanding the specs and writing the RTL code or the Verilog code, all of these things. Now, moving a little more ahead with little more complexity, adding another layer of complexity to your chips, is the low power design. Okay, so if you see nowadays, the kind of power consumption that our chips are having is very minute. Previously, you wanted to try to charge your phone or your laptop, it was taking a lot of power, and the battery life was also very less. But now if you charge your phone once, you might also end up using it for 24 hours. If you're not into a lot of gaming and a lot of those things, you can aramse use it for 24 hours. You see that 1000 watt battery, this battery, that battery, mAh batteries, 20,000 mAh batteries, all of these things are coming into picture. So it means that you are adding more power capabilities to your chip, okay? And what does this low power design mean, okay? So now we have to go back to our transistor basics. See, you are just an RTL engineer, but till now you have touched upon back end, front end, now you are talking about transistor level, understand? So that is the kind of understanding you should have. Now if you go back to your transistors, so if you see this, so this is your gate channel, correct? So this is your this is the gate that you have, gate channel, okay? So this is the one which will push the electrons from one end to other end, correct? So at the end of the day, all your flip-flops, all your gates, everything are transistors, okay? This is the final leaf level implementation that will happen in your chip, your transistor. So you would have seen that Qualcomm, like Apple came up with a 3 nanometer chip. This guy came with a 1 nanometer chip. Arey, vaadu 5 nanometer chip chesadu, I am going and buying that. What does all that mean? This gate width is what it means. Lesser the gate width, faster the electrons will move from one end to other end. Obvious, right? If you increase the gate width, it will be slower. Now slow and fast is not something which your eyes can perceive, obviously. You will hardly have any difference when you are using a 5 nanometer chip and a 1 nanometer chip. You can't even make it out. Except you are using it for high complex problems where you want to like reduce the computing time for serious calculations, on the fly calculations, where you need real time data for launching a rocket or any of those things. Until you go to that level of precision, you cannot perceive the difference between the performance of a 3 nanometer or a 5 nanometer chip and a 1 nanometer chip, okay? But anyhow, this gate width is what defines which nanometer technology it is, okay? Now who will give this technology, what will happen, this is again a different story. So let's not get into that as of now. But now this channel width is what will come into picture. Now depending as we go to lower tech nodes in terms of the transistors, as designers we should make sure that our designs are supporting few things so that when it goes for the back end implementation, the design will not collapse. Got it? So that is, to put it in a very simple way, some low power designing there, okay? So what we do is we build something called as a UPF or a unified power format, where again we do lot of low power checks at the front end itself, okay? See, what happens is, as I was saying, the quality of the chip gets tested at every stage, okay? Let's say for example, in my chip cycle, this is the RTL or the design phase, okay? So parallel to this, your DV or your verification happens. From here, what I said, we will go for synthesis, correct? So your HDL is converted to gates. So here then you will go for PNR, which is place and route, then your actual GDS forms. GDS2 is what we call it, okay? So here again this is nothing but placed onto a die. So the floor plan diagrams that you would have seen on a real time, after synthesis is what it is generated. Now let's say there is some issue here for you to fit in 2 transistors or 2 blocks. You are not able to do it. Then you go back, you try to identify, you will be like, array, this design is not optimized, or this port is extra, or this pin is something which is causing an issue, or this logic is redundant logic which came into me. So then again you have to go back to the RTL guy, he has to fix his RTL, then it has to be converted into synthesis, and then it has to come to the PNR guy. Now that all of this has changed, the DV guy has to run bunch of tests to make sure it is clear, and then we were talking about some flow checks or quality checks before. Then the RTL guy also has to parallelly do all those quality checks, flow checks, to make sure nothing is broken, and that is when it will be passed on to the end. So this turnaround time or this turnaround period will affect your project deadlines, okay? And for the time to market that you are making will go up drastically. So you might as well end up being out of the market because your chip manufacturing will get delayed, because the moment you decide to do a chip, we call this GDS2, coming to this GDS2 level, as a tape out of a chip, okay? So this is called a tape out stage. It means that my chip is ready to go to a fab. It is ready for fabrication, okay? This tape out should happen on dot, because the fab guys, you will book the fabrication, the foundry or the fab for 2 months or 3 months to manufacture your chip. You lose that time slot, he will not give you the time slot till he is free again. And we already know there are hardly 2 or 3 fabs in the entire industry. So it is like you have the product ready, you cannot make it a chip, and at the same time your competitor went ahead and made that chip. That's all. The effort of what you have put through the entire 6 months or 9 months is gone for a waste. You cannot do anything with that design. Either you have to add some new features, you have to scrape it out and start a new design altogether, okay? So your entire hard work is gone for a waste, correct? So one mistake here, you are knocked out of the industry, got it? That is why what we do is, we try to do predictive analysis of the issues that can happen at different stages way ahead, okay? So that is where this UPF helps us, or this low power checks or the low power designing helps us, okay? So as design engineer, I not just worry about designing my chip, I also try to run a bunch of checks or tests way ahead of the chip cycle beforehand itself, and I try to reduce my design issues which can probably pop up till the end of the chip cycle, okay? So after I do all of these things, I qualify my design, send it to synthesis and PNR, so that this will never happen. Worst case scenario, this will happen definitely. The previous stage to next stage, that back and forth can happen, but from the last stage to first stage should never happen, okay? So that is how a design engineer should think. So for you to think to that extent, even if you are not an expert in all the stages of the chip cycle, you should definitely be aware of what is happening at each stage of the chip cycle, so that you can do those quality checks, you can do those assessments way ahead, so that your design is intact, okay? I think, is it a bit boring? You want me to go a bit slow, or is it fine? Okay. So that is how on a day-to-day basis we think, we execute and we do our chips, okay? So now coming to what are the other competencies, or what are the other things you should know as a design engineer. So till now we spoke about how a design engineer should think, write the logic, implement everything. Now comes something very important called as domain knowledge, which no other chip cycle guys can have it. Even if they have it, don't have it, people will not mind. But a front-end engineer, like a design engineer and verification engineer, both of them should definitely have the domain knowledge also. What is a domain knowledge? Like, you should know about ARM protocols. So you would have heard in a lot of chips that we are using ARM CPUs, correct? So ARM is one of the company that came up with bunch of industry standard protocols, okay, which are used across the industry. Now why? Because chips will be reusable. One chip has to interact with another chip. Let's say you are designing a board. So now you are doing your final year project. You buy chip from ARM, you buy chip from Samsung, you buy chip from some other company, and you are trying to make all of these three talk. Everyone have their own companies, they will design the chips they want. Now if you ask them to talk, how will they talk? They will not talk to each other, correct? To remove these issues, what they have done is, we have standardized few things across the industry. So be it any company, be it any chip, whatever it is, there are few standard protocols that are used across the industry without question, okay? So you have to follow those standards and you have to use it for your chip to be able to be used at a system level, okay? So those are some of the ARM protocols. So these are all those kind of protocols only. So ARM protocols, PCI Express is something, one of the universal protocol that we have defined. Then Ethernet is one of the universal protocol that we have defined. And then again we have MCUs, which are nothing but your microcontroller units, okay? Then we have ARM processors, then we have GPUs, then we have few basic communication protocols like I2C, SPI, USB, Ethernet, okay? So all of these things together form a complete SoC. Now you can be a design plus domain expert on a certain thing. So now why you need these design expertise is because, let's say tomorrow I have to work on an SoC. Now I don't know anything about Ethernet. Now I have to go and work. Now I cannot just directly go and start working on it, because for me to understand the specification and where Ethernet fits in that chip, I should know what that Ethernet does, how it works, what capabilities it brings in. So for me to learn and design that chip will take a lot of time. If I am already a design expert in that, obviously I'll take less time. As soon as I start reading, I'll understand what is happening and I'll immediately get on to the job. So this domain expertise you should start gaining maybe after 5 years of the industry. So till 5 years you should learn how to do all of those things. After 5 years, along with that, you should also try to start coming up with your own domain expertise. So like I have the domain expertise of working around CPUs. Now I have worked on RISC-based CPU architectures, I have worked on ARM-based CPU architectures. Within ARM processors, I have worked on multiple architectures of ARM and all the IPs or all the subsystems interacting with these ARM CPUs. So for me, you give me any CPU based architecture SoC, I can quickly start working on it. Likewise, you can build your expertise on whatever is interesting for you, okay? So that way, these are few of the domains where you can slowly start building your expertise after a stage. Now this is the next level, okay? So here we are talking about SoC integration expertises, okay? So what is an SoC? So at the SoC I was telling that you have to tie down all of those things, correct? For you to tie down all of those things also, again you should have certain expertises and you should have certain knowledges there. So you should know how to analyze those requirements. Like I was talking, like what has to be placed where in the chip. So that analysis you should know. Again, you should be able to derive that from your specification document. And then your system partitioning, like how to partition your system, which has to be placed where. And then you should also know why it has to be placed in a certain place for better performance optimization. Again, it goes back to PPA. So let's say, for example, you have a house and you have like 10 rooms in the house. Your bedroom is in one corner, your washroom is in one corner. Does that make sense? No, it doesn't make sense, because your washroom should be within your bedroom, otherwise you cannot use it effectively. Likewise, your chip also, if two blocks are talking to each other and you place them at two different worlds or two different corners of the chip, the time for the design to interact or the blocks to communicate to each other will increase the time, directly decreasing your PPA, your performance of the chip. So that way, that's the reason you should understand how the chip works, understand what has to be placed and what two things have to be grouped and kept together. This expertise you will get only after a certain level of experience. Once you start understanding the spec, once you know the PPA, once you understand the entire cycle, once you know how the entire SOC works, so that is the kind of expertise eventually you should start gaining for yourself. Okay. So that is what makes you a overall design engineer, and it will take good amount of 10-15 years of experience for you to reach to that level of understanding, because you should have worked at least on 10 to 15 different types of designs and chips for you to get that level of clarity. Okay. Next, another key role a design engineer can play is clock architecture design expertise, because clock is like the heart and soul of your chip, and you should be able to build an most effective clock structure for your chips. Okay, because that is what triggers your entire design. Correct? Agreed? So that itself is a very good domain expertise or a skill that you can build within being a design engineer. Okay. So you can imagine, once you become a design engineer, you still have lot of different sub domains or sub things that you can pick for yourself to be an expert in. Okay. And the next is again low power design expertise is what I was talking about. So to reduce the power consumed by the SOC, we should be able to effectively design the chip to reduce the power and the power and increase the performance. So for that again, you should have some level of low power design expertise in terms of how to use all of these things, power gating, clock gating, lot of these design techniques that we use on a day-to-day basis. Okay. And the other thing is, okay, these are some tool expertises that you would need for your RTL integration. Okay. So these are some of the tools that you would require. This is something that eventually you will get to know, but these are also the expertises which our team had in terms of executing the chip that we were designing. Okay. Okay. So now this will be a little interesting for you guys. So this is a typical case study that we have prepared. So what we as a company do is that we are into design services. So we provide design solutions to all of our clients. So a client can come to us saying that we have a specification, we want your support to design this particular SOC or a subsystem or a chip. Okay. So for those things, we talk about our previous designs or the previous projects that we have handled in a very structured format. So this is one of that example. So if you see here, MCU design, meaning it's a microcontroller unit based design for an IoT application. So now if you see what is the, so here we are talking about what is the core. So CPU core subsystem is something that we have designed for our chip, and what kind of core. So again, it is an ARM M0 based design. So what kind of core we used, that is one thing that we will highlight. And then what is the skill that we have put into this. So since this is my case study, I have put it as RTL design. And next, what are the clocks that are used. So the more the clocks we have used for that SOC shows the complexity of the design. So this is somewhere between a mid to low level complex design, because it just hardly has 2 to 3 clock domains and 2 power domains, that's all. Okay. So it's a very basic chip. And what is the team size? I could achieve this chip with just three RTL engineers. And what is the project duration? So we finished this for 8 months. So when I say 8 months, till the backend is finished. So the RTL support will be required till the end of the cycle. So that is why we could finish this entire chip in 8 months. And what is the team experience? As I said earlier, 6 years. I mentioned in my first slide, right? So average team experience we had is what? 6 years. And then yes, this particular design was targeted for low power. Okay. And then what is it? It's a power critical design. And then it is a 5 million gate count design. Okay. So finally, what is the 5 million gate count is nothing but, let's say for example, finally after I do my synthesis PNR, if I see the number of gates that actually got implemented in terms of transistors or in terms of my flops, that is what is I call as the gate count. So that is what we call it as an area of a chip. Okay, area of chip is nothing but the number of transistors finally got implemented in that design. Okay, the more the transistors, the more the complex the chip is and the more dense the chip is. Simple. Now, so here I would like you guys to focus on 2-3 things. One is the power critical, and then the, okay, for now we'll talk about this power critical design. So if we go back to our PPA, so we were talking about PPA, right? Power, performance and area. So the moment I try to reduce my area, my power will go up, because power and area are inversely proportional. The minute I try to have a power efficient solution, that might increase my area. I cannot achieve both the things in one chip whatsoever, because it is against your law of physics, laws of transistors and physics. So as a consumer, I would tell you what is my critical point here. Do I want a, what is the point that I can compromise on? Can I compromise on area or can I compromise on power? That again depends on the end use case. So there will be, let's say for example, you are designing a chip targeted for a satellite. There, more than the, depending on which part of the satellite the chip is going into, it will be either power efficient or area efficient, correct? So when you are shipping off something to outer space, there even if the area is slightly more, the power consumption and the way it has to handle the power should be critical, because your entire system will run on some batteries that you fix and send. Or else there will be something where the satellite or the payload itself is a smaller one and you cannot increase the chip size. But you have some external power and you can give the power, but you cannot compromise on area. So with that analysis, they will tell you whether it's a area critical chip or a power critical chip. So the end customer or the person who is designing, who will be consuming this chip will tell you, I want a SoC or I want a chip which will have only this much power, or which will consume only a certain power range, or which has to fit into a die size of this size. Okay. So either I will work on gate count or I will work on the power consumed by it. Based on this, I will take my decisions in terms of how to design my chip. Okay. So this is one of the key factor. That is why I was always telling PPA is very important for us. Okay. Now if you see, these are some of the boring project details. So we designed a ARM based MCU system targeted for home or commercial based IoT systems. Okay. And then this particular architecture was completely custom made for this particular customer. And then what was our contribution for this entire design? So we generated the ARM M0 cores. So basically ARM gives us a tool to generate the cores. We need not sit and write the CPU cores by default, but we have to make a lot of customization. So it will kind of give you something based on, because as I said, ARM came up with these standards. It doesn't compromise on certain key functionalities of the cores. So it will generate those cores with some basic key features which cannot be compromised, and on top of it you can add bunch of layers of your customizations. So we did all the customizations for the particular design, and then we also designed the interconnect custom made for this particular chip. Again, the NOC there I was talking about, that is nothing but network on chip or the interconnect. It's simply like the bus we call to connect all the systems within the SoC. So those again needs to follow some standards. But for this particular chip, we did the whole design from the scratch because the customer wanted it in a certain way. Again, we used the standard building blocks, but we went slightly out of the traditional way of designing a NOC, and we did a custom design NOC for this particular design. And then we owned and developed the entire flow for the quality checks. So what I spoke about a lot of quality checks at different stages, right? So we owned the entire quality check processes and we did it. Okay, and finally there was a flash module that was used. So we had to build the flash memory IP and the controller for it. So that is something that we did. And finally we helped the top level team and all the other backend teams to close on the design integration and implementation till the end. Okay, so this is like a typical project flow. This is like a typical day-to-day activities which a design engineer does, and these are the complexities that we have to handle, and these are the different domains where we will be interacting and doing bunch of things. Okay, yeah, so that's pretty much I had for this. So now if you want anything in detail or you want me to go through anything specific, you want to understand a bit more on something, see, I can talk about this for next 2 days also, I don't mind, but it's an ocean. So if you are, so I just want you guys to give the feel of how things will happen on a top level for a design engineer in terms of the work, so that you would understand how to achieve a design. Okay, so now if you have any questions around this, please let me know. Yeah. Yes. So you just want to know the difference between UCI and PCI. You know it. A little about it, which is used where. Okay. So basically, let's say for example, these days we have these data centers, right? We have a lot of these AI, we have a lot of these data centers to enable our AI based activities, correct? Because you need a lot of back and forth data to be transferred, correct? So if you see a data center that is remotely situated somewhere, and your PC or your chip is sitting somewhere else, and in between somewhere this you will have a server that will connect your PC to the data center, correct? So this server which is sitting in between, which is connecting your end user's device, your handheld device or your laptop or whatever it is, to the data center, will have certain capabilities to it. Okay, now this particular uh, server, let's say we'll call it a server SoC. So this server SoC or this server chip has to quickly take your inputs. So that will go as a software command that will translate to a communication like a signal or a wavelength. It will transfer to that particular server, correct? That will again get translated internally to a digital form, and then that will get processed within the server, because your query needs to be processed, right? And that will again be translated into a communication signal, because it's all wireless, and then with lot of frequency hopping or lot of the thing, it will connect to the data server, get the data, follow the same step back, and give you the final output. But do you realize all this is happening in the background? No, right? You click it, you will get the data, correct? So it means it is working at that incredible speed that you don't even perceive as a human that it is working at that speed. Okay, for this high speed things to happen, these regular interconnects, like your like I was talking about this, right? I2C, SBI, USB, these standards will not support those speeds. So there comes your PCI. Okay, so PCIe is a high speed protocol which can operate at gigahertz of speeds, and which can transfer bulk data in and out quickly without even knowing for your computations. Okay, so that is where your PCIe and Ethernet sit in the entire ecosystem of your so this is a complete system, correct? From your PC to data center to your PC is called a complete system. Somewhere in this system is your SoC. Somewhere in that SoC is your PCIe, which is doing all this communication for helping you to take the input and give you the output. Okay, that is where your PCIe sits. On the other hand, UCIe is something which enables the communication between two chiplets. So SOC is one chip. Likewise, you have 2 to 3 chips to form a system. So now, till now we were just studying only till this level where we have a system on chip. So this one system on chip is called one chip. Likewise, you will have 2 to 3 chips to form a complete chiplet. So this chiplet, so you need again a high speed protocol, or you need a high speed standard for two chips to interact. That is where your UCIe will come into picture. It will connect two different chips basically. Okay. So within the chip you will have a PCIe, and outside the chip sorry, between two chips or connecting multiple chips to form a bigger system is where your UCIe protocol or your UCIe standard will be used. I hope I made sense. Okay.
I have a query. Like you told you are working on like CPUs and all those things. So I thought to do major project on network on chip routing. Okay, so I want to ask like when you design the CPUs with different cores like multi-core and many-core CPUs, how will you route like efficiently, like in traditional methods or different type of methods? What do you use? Because suppose if their network packet what we are sending is already be buffed in a way, so how do we manage those buffers in a high speed design?
Okay. So first let me simplify your question, then I'll answer your question. Okay. See, okay, let me put it this way. What is the need for multi-core, first of all? So first we need to understand why do we need a multi-core chip. So let's say for example, you have your latest iPhones or latest any of the mobiles where they say quad-core chips, multi-core chips, or they say like octa-core chips, correct? It means
Efficient cores,
efficient cores, you have separate cores for separate things, lot of these things. Okay, so the reason you need, and then comes the division like CPU, GPU, NPU, correct? See, basically what happens is you can do all of this with one core also, but the time will be more. Let's say for example, traditional chips or the laptops or the phones that we were using few years back had single core. That time what used to happen, you could not do multitasking. Let's say for today what you're doing, you are playing a game, parallelly you want to watch a video, you have an option to just swipe up, you will have a small insert kind of a window where you can still see the video and here you can still play the game, or you can still go online and you can still play the game. Now for you to go online, it's a total different path of data that the chip has, the hardware has to travel and get it done for you. And for it to run a program on the chip and play a game, it requires a specific things. So if you go back to your computer organization, we have something called as multi-threading, correct? So it has to parallelly process two different things. Now one CPU cannot do that. It can take a bunch of instructions, execute something, give it back to you. After that only it can do this and it can give it back to you. So if you go back and think of some old designs of CPUs and phones, the moment you swipe between one window to other window, the other program will stop and this program will start. So the CPU will prioritize based on the user input, what has to be processed, what need not to be processed at this stage, and they will start the processing. So now to increase the performance, what we started doing, we started introducing multi-core. Now I will use one core dedicatedly to perform some background checks or some background boot sequences or something, some applications that needs to be run in the background continuously for the design not to collapse, and I will use the capabilities of other chip to other core to perform some other activities. Okay. Now to answer your question, let's say it again depends on the end use case. Like let's say for example, you are trying to use this in your Xbox. At that time Even these two CPUs will not be sufficient for you. Then you need something called as a GPU there, because you have to process video there, correct? Your entire thing is dependent on the graphics or the video that you use. So let's say you are trying to kick your opponent, okay, you press the button, but there is so lag that that kicking action is taking a minute or two. You are dead by then and your game is done, correct? So for that, to avoid that lag, to avoid that entire thing, you cannot rely on the CPU anymore. Even if you have 2 cores also, that will not happen. So what you did, you took out that entire capability of processing the videos and you have given it to a separate processing unit called GPU. So the moment you get an instruction, it will decide whether it has to pass on the network, whatever you are talking, will decide whether it has to be passed on to a CPU or a GPU. Okay, so based on the packet or based on the input that is being received by your network, it will decide which core it has to go. Now you ask me, how do I efficiently design this, correct? So buffers, correct? So here the efficient design that I can do is increasing the capability of the NOC or the network on chip. I cannot play around with the CPU architectures here because those are the standards. All I can do is I can optimize the CPU in such a way that I am using it to its fullest potential. I can unlock its features or I can push it to use it to the maximum capabilities that it can go and use, okay. But again, that will increase my area, got it? So again, you have to make a trade-off whether speed is important, area is important, okay. So depending on that, either I will reduce the capabilities of my CPU by not using certain parts of the parts of my CPU. Let's say if that packet whatever I am transferring, it's just to transfer from one end to other end. I don't need the ALU capabilities of my CPU, correct? I am not doing any computing there. So I can just disable that part of my CPU. That way it will reduce the area, it will increase the performance of that CPU. But again, I need not have a CPU to do that. I can simply have a register to push my data. So that also is an optimized way of designing it. Got it? So that way, as and when we are increasing the multi-layer complexity of our end products, we started increasing the number of cores, we started increasing the type of processors that we are using depending on the end users, okay. So now if you have anything with AI enabled, you will also have something called as an NPU, neural processing unit. I think the latest iPhone had this NPU capability also. A lot of these current Samsung and Google is one of the company that is coming up with latest chips with NPUs enabled in that. So that way your AI capabilities will increase for those devices. Got it? So as and when this complexity increases, you can as well have your thing. So that is how, as a design engineer, I would decide whether to optimize it, use it, or completely remove it and replace it with some other hardware which can still do my work at a lesser cost in terms of PPA. Anything else? Boring? Girls, speak up. You're not talking. No questions? Okay. So maybe I can just try to show you some other boring stuff. Okay, so this is a typical chip cycle. These are some additional things that I had. So we discussed about all of these things, right? Collecting the requirements, product requirement and specification, architecture specification, and this is where we are, RTL design team. So all of these things will be owned by the RTL team or the design team, and anything beyond that is called the back end. So this particular thing is the front end of the chip, and this particular thing is the back end of the chip cycle, okay. And this is some basic difference between an FPGA and ASIC. I hope you all know about it, so I am not getting more into that. Simple funda, if you want to manufacture anything in terms of hundreds, like less than 100 pieces or like 10, 20s, you can go for FPGA, but because that is a readily available solution that will not burn a hole in your pocket. Anything that you want to go for mass production, bulk production, you know, can be consumed at a large quantities, you will go for ASIC based designs. As simple as that. And this is a typical FPGA flow in which it happens. So designing an FPGA based design and a ASIC based design will be different only in terms of implementation. So as a designer, it should not matter to you, because either it is going on FPGA or ASIC, your job is to write an optimal design, that's all. And then these are the different stages in the RTL design process which we discussed, like understanding the microarchitecture, gaining the domain specific knowledge, then RTL coding, then doing all the quality checks or the design metrics before you send your design to the next stage of the chip. And then the next stages is nothing but synthesis, timing constraints, your DFT, and a lot of other things. So this DFT is one more interesting thing. Since we are talking, I just want to mention about it. So DFT is something that we build a self-testing mechanism in all our chips, because tomorrow once the chip is manufactured, it might also have some manufacturing defects in it. So how will you before you ship your chip, you should check even for your manufacturing defects, right? So to enable those manufacturing defect checks in your chip, we include additional logic, which is nothing but a DFT logic, so design for test. So this particular part of the logic will be used only after your chip is manufactured, and to make sure that it doesn't have any manufacturing defects and it can be sent to the customer. Okay, so this is one more interesting thing we do as engineers. So this is again a different skill and a job opportunity that you can look for. Yeah, so this is something that you would be very much interested in. So like even for the uh, so to understand what experienced man has, what kind of expectations in terms of technical skill set and in terms of other skills. So this can be like a guiding point for everyone to understand more on the industry level experience. Yeah. Yeah. Okay. So that's pretty much I had in mind. I think if you have any questions, we'll go ahead, or else I think we can wrap it up. Any other questions? Okay. Thanks guys. Thanks for being a lovely audience.
Ma'am, any internship opportunities are there with your company for our students?
Definitely. So you just have to keep following our SmartSoc page on LinkedIn. So we would be posting as and when new internship opportunities keep coming up. It is not like a fixed cycle that we hire this time of the year or anything. Based on the project requirements, suddenly also we start hiring. So this is something that you can keep following our page and you will get more insights. If I get any heads ups, probably I'll just trickle down that information to our lecturers and they can let you know if something is coming up. Okay?
If you want to make this, hands-on experience like system developer verifications, which design would need to be practiced before going to coding kind of things? Any standard designs you work on that means we can learn all kind of parameters.
Yeah, so I would say like if you understand one CPU architecture, that is like a very good start point for you, because one CPU architecture, understanding a CPU architecture in the sense like what happens from input to output, how is the entire data path and the control path from fetch to final execute. Okay, So that entire data path, how your input translates at different stages, if you are able to explain that with timing diagrams, that will be like a very good, and it's like, because your CPU architecture is like a big umbrella of all the architectures. Like one, if you are able to figure out one such flow, you will be able to figure out any kind of designs very easily. Okay. Otherwise, you can go ahead and learn about basic communication protocols like SPI, I2C, UART. These are very simple to understand. So
AMBA,
the AMBA,
protocols.
AMBA
And what
protocols.
kind of parameters we need to consider in generally in system developer verifications?
So verification, anyhow, you have a detailed session next. So there you will cover more on the verification side.
Free sites, document kind of.
Yes, so maybe after that I'll pass on some of the free data that is available, free sites that you can explore. So there are a lot of online tools also that you can explore just to run and check your designs. So probably we'll just pass on that so you can share it with the students. Yeah. So you can do a lot of things online. You can try to understand and get things done. See, again, the start point should be for you to understand the design, come up with one RTL. So until after that, you can slowly build on verifying it, system verilog, a lot of these things.
Only we require interest. Everything will
Yes,
be there.
yes,
So we
yes,
need to find it.
yes.
Questions? Little that. We require some discussions. I'm waiting for HOD sir. That's it.
Sure.
Language also most important.
Yes, yes, definitely you would need scripting on a day-to-day basis, because see, at the end of the day, these designs are so complex, so you would need lot of data processing to analyze your outputs for all these flow checks, lot of these things. You cannot sit and manually do it. The size of one report will be like 10,000, 20,000 lines. How will you grep, or like how will you come up with the data out of it to analyze or do your debug? So for all of these things, some kind of scripting knowledge will always be helpful. Yeah, yeah, sure, sure, no worries.
Thank you so much.
They're asking any tools or kind of thing.
Projects గురించి అంతే.
Everything interactive.
Students engaged, sir. Session is పక్కన ఉంది. అన్ని సెషన్స్ లో సెషన్ వాళ్ళ కోసం స్మాల్ ప్రెజెంటేషన్.
ఒక నిమిషం అబ్బాయి. హలో, వేర్ ఆర్ యూ? On the way, okay. Once you come, it. Okay, once you are.
పెట్టుకోమంటారా?
ఇది కూడా పెట్టుకుంటే అందరికి ఇదేమో లైవ్ హాయ్